Is Lab 3 for Physics 2211. So this was the lab where we coded a spaceship orbiting a planet. So the purpose was to estimate the mass of the black hole, or orbiting a black hole, and the purpose was to estimate the mass of the black hole, and then do a second simulation where we determine the initial velocity for a stable orbit around both the moon and the planet. So the methods we did this by was by coding in GlowScript. First we did well, actually, I'm just going to show you. Okay, well, fundamental physics principles was Newton's second law and all the derivations of it. So, which is like velocity equals, or final velocity equals initial velocity plus F net over m times the change in time, and then final position equals initial position plus average velocity times the change in time, and then F equals ma, and then the universal gravitation equation, which is negative g, mass of both things going on over the radius between them squared times the negative unit vector. So our results were that the mass was 1.0327 times 10 to the 34th kilograms. I didn't put kilograms, but I'm saying it now, so yeah. And then the initial velocity required was 2.4404 times 10 to the 4th meters per second. So this is my code where you start with the P initial is the mass times V initial, and then final is mass times V final, and then so delta V is going to be the change in from V final to V initial. Delta P is the change from P final to P initial. So dP dt is going to be delta P over delta T. F net is going to be dP dt. P hat is P initial over the magnitude of P initial. D mag P dt is the magnitude of P final minus the magnitude of P initial over delta T. dP dt parallel is the magnitude P dt times P hat. So F net parallel is going to be dP dt parallel. dP dt perpendicular is dP dt minus dP dt parallel. F net perpendicular is dP dt perpendicular. And so then to find the mass of the black hole, it's the magnitude of the net force times the magnitude of the star times the magnitude of the star squared, I guess, over the universal gravitational constant times the magnitude times the star mass. Which is how we got the number I said earlier. So to track it, we watch this vector and then put all these arrows in there, which I'm gonna go over to the is this the right one? Yes, this is. So this is where we run it, and you can see the arrows representing the forces acting on it. So yeah, I thought that was pretty cool that worked. So then for the second part, which was the planet to the moon, here's the starting of it where we were finding the position of the moon in regard to the planet and then finding the unit vectors for them, which then we find the planet, for the force of the planet on the moon. So we found that force of the ship on the moon, then force of the planet on ship, moon on the ship, and then from that we could get the ship speed and velocity, and then the moon velocity in position and ship velocity in position. So when I actually ran this, it ended up kind of looking like this, which I know is not perfect, but at least it didn't crash and, so actually, if I keep running it, it keeps going in a spiral like it's going like, and it just goes forever. So I just cut it here. So, that's the best I could get because I was doing this at about 1 a.m. So that's what we got. So the conclusion is possible errors. There's obviously, I have a very surface level understanding of Python. It's not amazing. And then, as I said, running the simulation for the second part longer shows that the path goes really wonky. And so the questions is, how is net force not the same as the rate of change of momentum? Because as you can see in the simulation, the arrows were not identical. They weren't doing the same thing the whole time. They were pointing in slightly different directions because rate of change of momentum is literally just fundamentally different than net force. And then if we considered everything to be the system, we would have to kind of zoom out a lot and figure out other things that could be considered the surroundings. And then we would also have to consider inside of the system how all of those would work on each other and affect the movements of each other because that would move the entire system around. Yeah, that's it. Thanks.